Check. Check. Okay, let's go ahead and begin. Notice I have posted solutions to midterm 2. Just like last time, I suggest that you take some time to go over these solutions before you get your paper back. Read them carefully. Maybe grade yourself mentally. Prepare yourself for whatever grade you think you're going to get. See if you get that grade and see where it departs. I always get a lot of questions from people saying, I don't understand what happened here. I don't understand what happened there. And then my first question is, did you read the solutions? And very often the answer is no, I didn't actually look at the solutions. So please spend some time studying these solutions and do so, to prepare for the final exam also. Okay, I hope you agree it was a pretty doable exam. I think it'll probably turn out okay for most people. Question? Go ahead. It's a 3-hour exam. I don't mean to say that it'll actually take you 3 hours. More like, well, let's put it this way. If it was supposed to be, this is 65 minutes. So if I were going to scale it the same way, I would have, at least 13, maybe 14 problems for 3 hours. There's no way I'm going to give you anything over 10 problems because there's no time, we don't have time to grade that many problems. So you'll be under considerably less time pressure on the final exam than you were on any of these midterms. Okay. What else? Homework 8 is posted. For the first time in a long time, I've got a homework 8 that's going to be graded, but I'm giving you a respite from homework. We should get our homework 7 back sometime this week, but this one is not due until Monday. I decided to give you a long time to complete it, and me a long time to get through the material that we need to cover for you to be prepared to do these problems. There will be a homework assignment 9 that you will not turn in. It will just be more review. I'll post the solutions as soon as I post the problems, right? It's more just review problems, kind of another set of review problems, which we'll call homework 9. Okay, so that's where we are, PA 5. Maybe I should take a few minutes to talk about, wait. I'm in the middle of talking about PA 5 right now, so let's get to the end of this. Okay, 23.5, this is where I ended last Wednesday, strongly connected components. Remember, a subset of the vertex set is said to be strongly connected if given any 2 vertices in that subset, you can get from one to the other and back, right? You can get from anywhere to anywhere. That's what strongly connected means. Okay? And more specifically, a subset is called a strongly connected component. This is more than strongly connected. It has to be strongly connected, but it also, to be a component, strongly connected component, it has to be maximal with respect to the property of being strongly connected. Remember what the word maximal means in mathematics. It means you can't get any bigger and retain the property. Notice the more vertices there are in a set, the harder it is to retain that property, right? Because you've got to get from anywhere to anywhere. Add a vertex to a strongly connected set. You're adding a constraint when you say you got to be able to get from anywhere to anywhere. You got to get to that new point, and you've got to get from that new point anywhere in the existing set. So as you add vertices, you're making property 1, strongly connected, harder to maintain. And maximal means you have a set that you can't add anything to and retain property 1. Those are the strongly connected components of a digraph. Everything here is about digraphs. So DFS can be used to find the strongly connected components. It's very similar to using DFS to do a topological sort of a DAG. Of course, this applies to any digraph. It can have directed cycles or not. Okay. By the way, what are the strongly connected components in a DAG? We mentioned this last time, but I wonder if anybody remembers. Say again? The singletons, right? The subsets of the vertex set consisting of just one vertex. Those subsets are the strongly connected components in a DAG. Because in a DAG, you can never get back once you leave, because there are no directed cycles. Make sense? So you can, in a one-element subset of the vertex set, you can certainly get from anywhere to anywhere. All you have to do is travel along the trivial path with no directed edges. But you can't get any bigger. You can't add any vertices because you can't go somewhere and get back. Otherwise, it'd be a directed cycle. Okay, so DFS can be used to find the strongly connected components in any digraph. Run DFS. And do what you would do in order to come up with a topological sort, if it were a DAG. Namely, push the vertices onto a stack at their finish times. So as vertices finish, you push them onto a stack. Equivalently, you're sorting them by decreasing finish times. So at the top of the stack is the latest or largest finish time, and at the bottom of the stack is the earliest or smallest finish time. Okay? Now compute the transpose of the graph. That means reverse all the one-way street signs. Change all the directions. In terms of the adjacency matrix, that's the transpose of the adjacency matrix. Now run DFS on that transpose, but now we change our convention as to the order of the main loop of DFS. Instead of our usual convention, which is increasing vertex labels, we now run that stack by just popping vertices off the stack. The stack controls the order in which vertices are processed in that main loop of DFS. We still continue to process vertices in the for loop in visit by increasing vertex labels. But it's that main loop of DFS that changes. Okay. Theorem. When this is done, the strong components of G are the trees in the DFS forest. Okay, the only thing missing is an example. I have several examples here. Let me just, in the interests of time, I'm going to do exactly one. This example actually is, if you go back to, I was looking over my examples this morning. So examples PA5 in 7. So this is actually the 7th example. In 7 and out 7 are a matched pair of input-output files for programming assignment. Am I showing you the right thing? Yeah, for programming assignment 5. Okay. Before I forget, let me change that. Okay, so here's an example. The DFS to find SCCs. So let's do it the quick way. Rather than go through the adjacency list, let's just eyeball it. 11 vertices. Those are the labels. Here is everything but the directions. Now let's put those in. Is that right? Yes. Directions here are important. If I reversed just one direction, everything would change. You know, because the reachability relation would change. It would change who is reachable from who, and it would change the strongly connected components most likely. Okay. Boom. And then, okay, so there it is. So, the first run of DFS, so here's G. What's the order of the main loop of DFS on our first run? Well, it doesn't really matter, so let's stick to our convention the first time we run DFS. Namely, we're going to run DFS by main loop in DFS by increasing vertex labels, which means I start at 1. By the way, I've never given a test with DFS in the test where a student did not come to me and ask, what's the source to DFS? You didn't tell us in the problem what the source is. It's never happened that I haven't had that question on a test. You all know what's wrong with that question now, right? I'm not going to name the person. In fact, I forgot who the person was. Right, there's no source to DFS, so we have to have some kind of convention to know where to start. Okay, gray that vertex 1. That becomes a root. And then discover the lowest thing first. That's 2. So I gray the 2. That becomes a child of 1. Okay. Discover whatever I can, lowest vertex first. That's the 5. Gray that one, that becomes a child of 2. Discover whatever I can, lowest vertex first. That would be the 4. 4 becomes a child of 5. Discover whatever I can. Well, I can't discover anything new. So I blacken the 4, return to the 5, nothing new, blacken the 5, return to the 2, nothing new, blacken the 2, return to the 1, blacken the 1. Okay. I was going to shade the tree edges. Gets a little messy if I'm not careful about that. Okay, so there's the first tree. Now what? Now I'm back in the main loop of DFS. This whole stack of recursive calls has returned, and now I go to 2. It's already been discovered. Go to 3. It's not yet been discovered. So I discover 3, gray it, and discover everything I can from 3. Nothing. Can't discover anything from 3. So blacken that. You see? The only thing that it points to is 2 and 5. They've already been discovered. You can also see that these are necessarily cross edges because they go from tree to tree. Okay, so this guy is blackened. I'm again back in the main loop of DFS. Go to 4, been discovered. 5, it's been discovered. 6 has not yet been discovered. So from 6, I discover 6, it becomes a new root of DFS. I'm still going slow. I could be whipping through this if I wanted to, and you should get fast and accurate at it. Of course, I guess you did it already, but on the exam. I hope you were fast and accurate at it on the exam. Okay, so from 6, what can I discover that's new? Well, looks like 9 and 10, and 9 is the lowest. Discover 9 from 6. That's a tree edge. So I gray 9. Now what can I discover? It looks like from 9, the only thing I can discover is 8. That becomes a child of 9. From 8, what can I discover? Nothing. Blacken it, return to 9. What can I discover? Nothing. Blacken it, return to 6. Oops, I forgot to shade that edge. And what can I discover from 6? Oh, I can still discover 10. 10 is a child of 6. That's a tree edge. From 10, what can I discover? 11, that's all. That's new. That's a tree edge. 11 is a child of 10. Now what can I discover? The only thing left is 7 from 11. Gray that. Becomes a child of 11. That's a tree edge. And then return to 11, nothing, or I can discover nothing new. Because that's black and that's gray right now. They have to be white to be discovered. So blacken the 7, the 11, the 10, the 6, and then everything's been discovered. Or I'll continue on the main loop of DFS, which is 7, 8, 9, 10, 11. There's nothing to do there because they're all black at this point. Okay, so that's the first run of DFS. But I was supposed to do something. I was supposed to push vertices onto the stack as I finish. Okay, well that's not hard to reconstruct from this tree. What did we do? Discover, 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 finish. So 4 is at the bottom of the stack. Finish the 5, finish the 2, finish the 1, then discover the 3, then finish the 3, discover the 6, discover, discover, finish the 8, finish the 9, return, but don't finish because there's something else to be discovered. Discover, 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 finish the 7, finish the 11, finish the 10, finish the 6. That's the stack. And that order is what dictates the next run of DFS, the main loop of DFS. Okay, so what's G transpose? Same vertices. Think of these as two different graphs on the same set of vertices. So let's carefully draw the transpose. Okay. I'll do the directions on a separate step. Okay. I didn't miss anything, did I? And stop me if I make a mistake, please. Okay, did I do it all correctly? That is G transpose. Reverse all the directions. Now I'm supposed to run DFS again, except main loop is executed in stacked order. So, remember, as I'm processing adjacency lists, though, I'm still, it's still lowest label first. So we start at 6. We gray 6. Six is a root. And now I visit 6, and what can I discover from 6? It looks like the only thing I can discover is 7. And from 7, the only thing I can discover is 11. And from 11, the only thing I can discover is 10. And from 10, I can't discover 6 anymore. So I guess I'm going to continue to shade the tree edges, but okay, so I return. They're all black now. So that takes care of 6. Going down the list in order, 10 has been discovered, 11 has been discovered, 7 has been discovered. What about 9? 9 is the next one to be discovered. So 9 becomes a root. From 9, I can discover nothing new because the only outgoing edges go to 6 and 10. So 9 is by itself a tree. It's blackened and finished. Okay. So what's next after 9? 8. Discover 8. From 8, I can discover nothing new. So we have another sort of trivial tree in this DFS forest. So we blacken that. Takes care of 8. What's next? 3. 3 is the next thing to be discovered. Again, I'm going down this list in order for the main loop of DFS. So 3 is a new root, but can I discover anything new from 3? No, I can't. So 3 is blackened. 3 is done. Okay, the next thing, so I'm back again to the main loop of DFS, go to the next iteration, discover 1, because that's the next thing in the list in order. From 1, finally, I can discover 4. So there's a tree edge. From 4, I can discover, looks like there are no choices, are there? There are no, in these, in the for loop in visit, I keep saying that's still going to be executed in increasing vertex label order, but that hasn't come into play. I haven't really had any choices. Okay, fine. That's a coincidence. So 4 has child 5. It doesn't look like we're going to have anything, because the only thing that can be discovered now from 5 is 2. Discover 2. Really discovered everything now. So blacken, that's a tree edge. Return, blacken, that's a tree edge. Return, blacken, blacken. Okay, everything has been blackened. Discovered, grayed, started white, grayed, and then blackened. Okay, so this is the state of the DFS forest after this second call to DFS on this new digraph. What are we supposed to conclude? What does the theorem tell us? It says that the vertex sets 7, 10, 11, all right, 6, 7, 11, 10, the singletons 9, 8, 3, and the set 1, 4, 5, 2, those subsets of the vertex set of the original graph are the strongly connected components in this graph. In other words, 6, 7, 11, 10, that is a strongly connected component. Clearly, if you have a directed cycle, all vertices on that cycle must be contained in the same strongly connected component. Think about it. You can surely get from anywhere to anywhere along that cycle just by traveling around the bus route, right? Get on and get off wherever you feel like it. But notice that once you leave that group, you cannot get back into it. You can't get back to it. Okay, so that's a strongly connected component. Furthermore, 9 is a strong component. And then, is that clear? I can get into 9, I can get out to 9, but once I get out, I can't get back in. Just eyeball it. Same with 8. I can get into 8, I can get out of 8, but once I get in, I can't get, once I get out, I can't get back. So that's a strong component. Likewise, 3 is a strongly connected component. There's 2 ways in, 2 ways out, but there's a directionality here. And then finally, the group 1, 2, 4, 5 itself is a directed cycle. So it forms a strongly connected component. Again, any directed cycle, all vertices on that cycle must be contained in the same strong component. I mean, you can have sort of interlinking directed cycles so that the strong component can have more than one cycle in it. In this case, that doesn't come up. Okay. Oh, I forgot to check these off. Okay, so these are indeed the strong components, and that's what the theorem told us they would be. Okay. So the theorem works. Well, that's what I've just done now, is to just demonstrate that it did work, at least in this case. Proof is in the book. I'm not going to go over the proof. Now, you have to write a program that does everything that I just did, and it needs to print out the strongly connected components. And it has to print them out in a specific order. What order is that? So here's another definition. The component graph of a digraph G, also called the condensation graph. Denoted GSCC is a new digraph with vertex set of GSCC equal to the set of strongly connected components in G. So each strongly connected component of G is one vertex. So in other words, all these vertices in one component sort of coalesce into a single new vertex. And all the vertices in this strong component coalesce into a single new vertex. That's why it's called condensation. Also, if Ci and Cj are in the vertex set of the condensation graph, there is an edge from CI, component I, to component J in this component graph, if and only if there exists an edge in G from some vertex in CI to some vertex in CJ. Some X in CI to some Y in CJ. So let me just kind of depict that like this. So if you have in G component I and in G component J, a vertex X in CI, a vertex Y in CJ, and a directed edge from X to Y, then this directed edge and any number of other directed edges from CI to CJ give rise to one directed edge in GSCC from this vertex to this vertex. So any other edges from this component to this component all coalesce into a single edge. You see what I'm saying? So we collapse a bunch of vertices into a single vertex. We collapse a bunch of edges into a single edges to get this component graph. Now, notice something about GSCC. GSCC is necessarily a DAG. It must be without directed cycles. Can someone please tell me why? So, say it a little louder. I'll just repeat what you're saying. Okay, so what he's saying is, if I could get in GSCC from CI to CJ, and then back from CJ to CI, in other words, if there were a directed cycle that contained these two vertices in GSCC, then that would imply the existence of a directed cycle that involves vertices in both CI and CJ, which would mean I could enlarge CI and CJ into a larger, strongly connected subset of the vertex set. But that's not possible, correct? That's not possible because these are strongly connected components. They can't be enlarged and maintain strong connectivity. So there cannot be a directed cycle in GSCC, this condensation graph or this component graph. If there were, then your strong components aren't strong components. Okay. So it's a DAG. What do DAGs have? Somebody tell me. What can you always do to a DAG, to the vertex set of a DAG? You can topologically sort the vertices in a DAG. There's a topological sort. So therefore, there is a topological of these vertices. I'm putting vertices in quotes. because the vertices are really subsets of the original vertex set. Okay, so you are required in PA5 to produce a topological sort of these strong components. That would seem like more work to do. You got to run DFS again on GSCC, the component graph, push vertices onto the stack, and that stack gives you the strong components. And I guess I could ask you to do that, right? You would have to somehow compute the adjacency list representation of the strong components of the component graph, and then operate DFS on it and produce a topological sort of its vertices. All of that is unnecessary, though, because we've already run DFS twice, and that's enough. The topological sort has actually already been computed. How? So, PA5 requires SCCs, strongly connected components, to be printed in topological sort order. How do we do that? How do we compute that? There we go. Well, we've already done it. Here's how. We've already written DFS in such a way that it pushes vertices onto a stack as it finishes. All we have to do is examine that stack after the second call. Right? The first call, we didn't really care what order we did the main loop of DFS. We saved that information, though, onto a stack, and that dictated the order in which DFS runs in the second call. So, the state of the stack, let's go back here, in the second call, is what's going to give us the topological sort. Look, discover, 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 finish, 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 discover, finish, discover, finish, discover, finish, discover, 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 finish, 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 finish. There's your stack from the second call. I mean, why bother to write the stack down from the second call? Well, you're not going to run it a third time. You don't have to run it a third time, so you don't really care about the order from that perspective. But that ordering does give you the topological sort. After all, let's go back to the original graph. And draw GSCC. Here's the original graph. So we have the group 1, 2, 4, 5. That is now one vertex. And I have yeah. I just want to see how I'm going to draw this. Let's just kind of draw it in an order that is sort of reminiscent of the original graph. Here's 3. Here's 8. Here is 6, 7, 10, 11. here is 9. Those are the strong components. By the way, notice that the strong components of G and the strong components of G transpose are one and the same. It has to be, because the reachability relation has been inverted, but the mutual reachability relation is exactly the same. Because if I can get from x to y and y to x in G, I can also get from y to x and x to y in G transpose. Okay. So those are the vertices. Let's see, I've got 2 edges going from this group to 3. They coalesce into a single edge. I've got 2, let's see, I've got 1 edge going from this group to 8. I've got an edge going from 8 to 9. I've got an edge going from this group to 9. Right, 2 edges actually. These 2 edges from 4 to 5 to 9, they coalesce into a single edge. What else? 9 to 6 and 9 to 10 coalesce into a single edge. What else? Do I have an edge? Oh yeah, I have an edge from this group to this group. That's from 5 to 6, so that gives me an edge here. And then what about, 2 edges from 3 to this group that coalesce into a single edge. Now, 1, 2, 3, 4, 5, 6, 7. Okay, so that is GSCC. All right, so what is a I see there's something wrong with my notes here. That's why I'm keep looking back at it, and I realize. Did I? Oh, I know the problem. You guys let me do it. I'm looking at G transpose. So I'm getting the directions wrong. I knew I was doing something wrong. Okay, so I have to throw this away. I wrote in pen, guys. Okay, so here's GSCC. No, let's throw that away too. Looks like this. Yeah. 1, 2, 5, 4, 3, 8, 9, 6, 7, 10, 11. Okay. Those are the vertices. Should have taken just 1 minute to do this, but somehow I managed to waste all kinds of time. Okay, so I can go from this to this. I can go from this to this. I can go from this to this. Right, that's actually 1 edge. I can go from 9 to this group. I can go from 8 to this group. And I can go from 9 to 8. What about 9 to this group? Yeah, from this group I can go there. There's GSCC. Okay, that is 5. Now what? Here's the, isn't there, well, first of all, notice there are no directed cycles. There better not be. Okay, so what is a topological sort? Actually, there's only one topological sort. 6, 7, 10, 11. That has to be first in the topological sort. And then what? I'm still confused. And then 9, and then 8, and then 3, and then 1, 2, 5, 4. Okay, let's just draw in all the edges. 1, 2, 3, 4, 5, 6, 7. Okay, so I have this going to 9 and 3. I have 9 to 8. I have 8 to this guy. I have 3 to this guy. And I think that's all. 1, 2, 3, 4, 5. No, there's 2 more. 9 goes to this group. And
6, 7, 10, 11 goes to 1, 2, 5, 4.
oh yeah, that's this one. Okay, now I have it all, right? 1, 2, 3, 4, 5, 6, 7. Okay, that's topological sort. Okay, how can I get that topological sort? So, this is how. Take the state of the stack after the second call and read it from bottom to top. 10, 11, 7, 6, 9, 8, 3, 2, 5, 4, 1. Actually, if I had just read it in order, that would have been correct. The only problem is, where does one strong component end and the other one start? How could you tell that? Well, that can be told by just noticing which vertices have no parent. So if I were to list the parents next to these, or the nil parents, 6 has a nil parent, 9 has a nil parent, 8 has a nil parent, 3 has a nil parent, and 1 has a nil parent. So you use those nil parents as sort of like dividers or commas. And that correctly divides it into strongly connected components. And it also gives you a topological sort. I'm not going to prove that. Notice that it worked in this case, though. Okay, and there's one last thing. And that is, how do you print... so how do you get your output file to match my output file? I want you to think about that. So if we go to output 7, 6, 7, 10, 11. So notice I'm printing the vertices in one tree from root to leaf. 6, 7, 10, 11, 9, 8, 3, 1, 4, 5, 2. That's the order in which I print them. So I print the components in topologically sorted order, but the vertices within each component are also printed in the order top to bottom. I don't think I mentioned this in the handout. However, I do want you to try to get the same output file that I do. So print them in this order. So how can you get that from the stack? Read the stack from bottom to top, and maybe put these things in a list and print out the list in order. Once you reach a nil parent, print out the list in order 6, 7, 10, 11. Nil parent, print out the list 9. Nil parent, print out the list 8. Nil parent, print out the list 3. Put these in a list, and then you reach a nil parent, you print out the list 1, 4, 5, 2. Okay, try to get my very same output file. The same order, the same topological sort. There might be multiple topological sorts, remember, of this, this component graph. Okay, well that's the one example I wanted to get through. And that's, oh yeah, how is all this accomplished? Maybe I should say one or two other things about the structure of PA5. In PA5, DFS takes a graph and a list, S. I refer to it as S because it serves as a stack internally. The order of S coming in dictates the order in which the main loop of DFS is to be executed. The order of S after it returns is a stack order, right? It's arranged now, same vertices, but by decreasing finish times. So you have to figure out how to do that. You have to use this incoming list for two purposes. One is to control the main loop of DFS. The other is to record the order in which vertices were finished by decreasing finish times. So there's a second call to DFS on G transpose, but the same S. So automatically, the fact that this records as an output variable and it dictates the order of the loop as an input variable, this is what accomplishes that task for you, right? The second call to DFS has to be done in a specific order. And also, the stack coming out is going to be used by you in function main to print out the connected components in strongly connected components in topologically sorted order, and to print out the vertices in the order I'd like to see them printed. Now, what order should it be going in order that we get the same output file? Numerical order, 1 through n, where n is the number of vertices. At this point, we're doing exactly the example I just did, and then the order coming out, so S is decreasing finish times. And then use order of S to print output. In the right order, right? Okay. Now, are there any questions on PA5? Any questions at all? Go ahead. So in my project description, I said there are a number of ways that you can implement the time variable. Okay. One kind of fancy way to do it is to declare time. I shouldn't even mention this because it wouldn't work in all compilers, but it does work in the GCC compiler. But if you're doing this on an IDE with some other compiler, then it might not be an option for you. But you could have time be a local variable in DFS, and then nest the definition of a function inside the other function. I'm not talking about recursion. I'm talking about nested function definitions. You've probably never seen or done that before because we never do it in Java. I don't think it's allowed in Java, but for some odd reason it's allowed under GCC in C. So some C compilers will allow it and some won't. And if you put things in the right order, then that time variable becomes global with respect to the interior defined function, which is what you want it to be. You want T to be basically a static global variable over all recursive calls to visit. Okay, everything I just said, forget it. I don't want anybody to try to do that. Here's what I think is the most straightforward way to do it. Pass in time by reference. So make it a local variable in DFS and pass it by reference into visit. In other words, you pass the address of time to visit. So you write visit in such a way that it takes another argument, not an int, but pointer to int. A pointer to int argument. That gives visit the ability to change the value of time at all levels of the recursion. Does that make sense?
Yeah, that was
Oh, good, okay. I was afraid nobody understood anything I'm saying. Okay, but good. Any other questions? Go ahead.
Explain how the stack
Yeah, let's go back to DFS. I wonder if I can find the day. Here, let's do this. Notes. So, where did I cover DFS? Was it here? Really? On the 24th? Okay. No, I think I'd already done it by the 24th. It had to be 22. Come on. There it is. So that's BFS. Doggone it. You're right. 24. Right. Here we are. Okay. So there is DFS. So we're talking about this loop, 5, 6, 7 in DFS. You've got to translate that into C somehow. All right, you're going to write DFS so that it takes a graph reference variable as an argument, but also a list reference variable as argument. So there's going to be another list parameter in DFS. Okay, that's S. So S is going to control this loop. So how do you do that? How do you traverse a list? You know by now how the list ADT works. Move front list, while index list, whatever you call let's call it S for now, okay? Move first S, while index S greater than or equal to 0, get something S, and then move next, right? So that's one way to do it. There's more than one way to do it. The real problem is, how do you do both at once? You basically use list operations to get through this loop. So I would expect it to be a while loop. I'm not writing the code for you, but do you see what I'm getting at? The order of that list is what dictates the order of this loop, and you have to use list operations to make that happen. Any other questions? Nobody's acting like they understood what I said, but I don't know. If I don't get a question, I can't say anymore. Go ahead.
Can you talk about the philosophy behind this algorithm?
The philosophy? Well, the philosophy is that it works. I mean, I don't know. When you say the method, are you talking about the theorem that says that that this procedure works? The theorem that says that you're going to get okay, so the book proves that if you do, it proves this theorem, which I stopped at. When this is done, the SECs are the trees in the DFS forest from the second call. Okay, without stopping, which it's enough, we're far enough behind. I can't prove that in class. So the philosophy, as you say, is I think what you mean is the proof. You have to read the textbook in order to get that proof. Why does this work? The book, however, doesn't prove that what I just told you works, namely that you're not only going to get out of that stack, the stack after the second call is actually going to give you the topological sort. It's kind of alluded to in the proof. All right, I can't really tell you how it works, because that would basically take another full lecture. Why it works, right? That's the proof. What next? Okay, so are there any more questions on how to get PA5 done? Go ahead. It's not a PA5. What is it, a kind of question? There are lots of uses for DFS. So the answer to your question is yes. What are they? Yeah, you can find the biconnected components in an undirected graph. What are biconnected components? Sorry, this isn't a graph theory class. It is a graph theory class. But, look, we learn a lot of graph theory in this class. Most classical problems in computer science can be stated in terms of pure graph theory. And I urge you to take a pure graph theory class. But that's not all we are. And I just can't keep going. But there are lots of uses for both DFS and BFS. There are hybrid algorithms that, sometimes act like BFS and sometimes, intelligent search algorithms. A lot of AI algorithms are kind of hybrids of these searching techniques. You amongst all your choices of where to go next, how do you make your decision? In DFS, it's just go as far as you can into the graph and then backtrack out. In BFS, it's stay as shallow as you can in the search before you go any deeper. And then there are, those are in a way the opposite extremes, but there are many many choices or many strategies that lie in between those two extremes. And a lot of, AI search algorithms like, Google's, what do they call it? Their indexing algorithm. Utilizes very intelligent combinations of these strategies. Beyond that, I can't really say much. Okay, so we got to keep going. You do have quite a bit of time left on PA5, do you not? So let's talk about B5. That's Appendix B5, rooted trees. I'm not out of time yet, am I? I am in a couple of minutes, huh? Well, we already talked about trees. Let's talk about rooted trees. A rooted tree is simply a tree that has one distinguished vertex called the root. each node can have any number of neighboring nodes. So I'm going to label that R because it's the root. I'm not going to label everything. So once you have distinguished a vertex as the root, it allows you to make more definitions. For instance, the distance from the root is the depth. We've talked about this. The root is at depth 0. Depth of a, by the way, I usually use the word node when I'm referring to a rooted tree, but there's nothing special about that word. It's synonymous with vertex. And every node has a unique parent, and that's the vertex that is one step closer to the root than it is along the unique path from that vertex to the root. Remember, in a tree, there's got to be a unique vertex a unique path from here to the root. The first thing you hit on that path is your parent. So every vertex has a number of children. Every vertex has only one parent, except the root has no parent. Now we can talk about ancestry, right? X is the parent of Y. It's the parent of Z. Z and Y are the children of X. And if I were to call this vertex W, Z would be the uncle of W. So I'll use statements like that. These are the leaves. Am I out of time yet? Leaves are vertices that have no children. Non-leaves are internal nodes. I will stop right there. Just need to define a bunch of terms to say everything we need to say. We're going to talk about heaps, by the way. It's chapter 6, I believe. I'll talk about that on Wednesday. Go ahead. Yes. Actually, a vertex is considered its own ancestor. It's its own descendant and its own ancestor. It's not its own child. Good. Sure.
So when we were looking at this stack
Yes?
and we were writing down the order,
Yeah.
does it have to be 1, 4, 5, 2, like we said 1, 2, 5, 4?
Well, when you